everybody, welcome to IRS Science Academy. Today I am going to start a series of lectures and the motivation of this series is quite interesting in the sense that this series takes into account some important mathematical concepts and their applications in the real life. So why I am starting this? This is the main thing is that when I was studying in the school, so in the beginning when we started doing plus minus and started learning numbers, it was quite clear that they are used in counting. But when we moved to higher classes, I noticed that there are certain concepts which are not clear where they are actually used in real life, and so this in this series I would like to educate the school students who are learning the um, some mathematical concepts, and this series also targets the teachers, math teachers, so that they know what they are actually teaching to students, where they are these concepts are actually applied. So normally what happens is that the teachers belong to pure mathematical fields of study, and they really don't know whether these mathematical concepts are applied. For example, they don't have engineering applications in their mind, and that is when actually delivered to the students. The students also feel this lack of lack in the concept, that they really don't know why they are studying these mathematical concepts, where they could have been applied. So that's why the mathematics teaching remains ambiguous, and I would say pretty uninteresting in my point of view. That's why I am going to bridge this gap. Therefore, I am starting with the matrix inversion, the most common concept. I think the first concept that is taught in the school when you move to 9th, 10th grade, or even the first year, 11th or 12th grades, and even higher when you move to bachelor's. If you are not from engineering field, it's very hard that you know about where the matrix inversion is actually used. So now I am bringing in front of you a very interesting application, and this application is very important because you are used to it every day. You have your smartphones in your hand, and the matrix inverse is used there. I will explain how it is used. I will first make a mathematical model, and then from that mathematical model I will tell you how actually the matrix inverse is being used in your common life, in every person's handheld device. So keep following me, and I will bring you interesting stuff. So the next thing is, what is the content? So I will start about the basics, the very basics of matrices. I will explain it in a simple way. I will tell you what are the rows and columns, and then I will explain you the difference between singular and non-singular matrices, and then I will come towards mobile communication system. I will model it as a linear equation, which you have seen in your school mathematics books, and then how this linear equation is used to when we solve this linear equation, then what we get at the end. Then I will compare the performance of singular and non-singular matrix, and finally I will conclude my presentation. So let's start. So the fundamental concepts. So what is a matrix? A matrix is when you read from the books, it says that you have square brackets, and within these square brackets you have some numbers. They could be real, imaginary, complex, or any number in between that. So A, B, C, D could be any numbers. And the numbers that are arranged in this row-wise fashion, they are called rows of a matrix. So here the A and B form the row of a matrix. And this and when numbers arranged in a vertical order, for example A and C, these are called the columns of the matrix. So here in this matrix you can see we have two rows, A, B and C, D. The second row is C, D, and similarly we have two columns, A, C and B, D. So this is the fundamental concept, and it is actually the definition that is written in a book, that numbers arranged written in the square brackets, and they have and these numbers could be real or imaginary or complex, whatever they could be. So they these numbers, they are also called these rows of a matrix are also called the row vectors. So how they are called row vectors? So for example, you see if we have A is a real number, B is the imaginary number, then we can form a vector A plus iota B or JB. And similarly, another vector could be C plus D iota or JD. So here in this case you can see that when the two vectors A, the vector one vector A plus iota B and C plus iota D, when they are perfectly pointing in the same direction, irrespective what size they have, the magnitude of the vector, so the magnitude of the vector could be different, but if the direction is exactly the same, the both vectors are pointing exactly in the same direction, then this will make a singular matrix, because both vectors are pointing in the same direction. We don't have any extra, and they are from one vector the other vector can be created. So if you multiply C plus JD with some real number, you can come up to the A plus JB. So you have exactly the same phase and the same information. So that's why these vectors are singular. When we have certain, if both vectors are pointing in different direction, then this matrix is called a non-singular matrix, because it contains two vectors which are pointing in different directions. So in this case, so a perfect singular matrix has a determinant 0. So I call this H1. But if you have a slight difference between the directions of these two vectors, then your determinant is non-zero, and it becomes, in this case, the determinant, I called it H2 matrix. The determinant is greater than 0, which is the H1, which was this case. And if these vectors are perfectly perpendicular to each other, then perpendicular to each other are in the physics way orthogonal to each other, then the determinant is highest. So this is a perfectly non-singular matrix in that case, if the vectors in that matrix are perfectly orthogonal to each other. The next, as I promised, I will explain, I will model a multi-antenna wireless communication system. So I will show you some known entities. For example, you may have seen that we have towers which in a particular community who is transmitting the signal, and I assume that this tower has two antennas. So you see TX1, TX2, so these two antennas are used to transmit. And on the receive side, we have our own fancy mobile phone. And I also assume that this mobile phone also has two antennas. So the tower is transmitting. This tower in mobile communication term, we call it a base station. So in the subsequent presentation, I will call it as a base station. So base station has two antennas, and mobile phone also has a two antennas. Base station is transmitting, and the mobile phone is receiving. So when base station is transmitting, there are four options. So the receive antenna on mobile phone gets signals from transmit antenna 1 and transmit antenna 2, and similarly the receive antenna gets transmit signal from antenna 1, I call it B, and the receive signal from transmit antenna 2. So these A, B, C, and D are actually the coefficients, the path coefficients we call it in the wireless technology of the channel. So in the simple way, we can say that we have transmitted signals S1 and S2, and they go through wireless channel. And then on the receive side, on the mobile phone side, we get Y1 and Y2. And wireless channel is nothing but just a matrix. You can see it's a matrix A, B, C, and D, which I have shown you earlier. So whole of this thing, we can model it as a matrix. So it is a matrix, and it is a wireless channel between the antennas of transmitter and receiver. And transmitter has our base station has transmitted signal S1 from antenna 1 and S2 from antenna 2, and this is written it like that. And then on the receive side, we get Y1 and Y2 as a vector, column vector. So this 2 by 2 matrix multiplied with the column vector of a transmitted signal, we get on the receive side y1 and y2 as a column vector of receive signal. And then you would be very surprised that we can write all of this thing as just a linear equation, which you have studied in your um, uh, ninth class, when you have studied the matrices. And even the first year student in Pakistan or India or any other country, the 11th grade students, they also come up with these kind of a linear equations where we have a y vector, and it is equal to the channel matrix a matrix multiplied with the transmitted signal. So these equations are very well written. So uh, this shows that actually a wireless communication system can be modeled as a linear equation. So now what to do with that linear equation? So the simple thing is the simple thing is that on the mobile phone side, we would like to extract what the base station has transmitted. So on the receiver side, we would like to see what was transmitted from the base station side, because this is actually the mobile telephony that we would like to get what has been transmitted. So mobile, as I have shown earlier, we have received a mobile phone has received the signal Y1 and Y2, and now he would like to get back S1 and S2. And how you can do that? So the very simple solution, solve the linear equation. So the only simple way is that this mobile phone side processing, this red box, you will see that it just needs to multiply this received signal with the H inverse matrix. And when we multiply the received signal with H inverse, then what would you get? So after solving this linear equation, you get the transmitted signal. So that's all actually, that you have recovered there is a transmitted signal S1 and S2 from the signal that was transmitted from the mobile station. But since all of you know that actually uh, computing a metric in inverse is quite challenging, especially when the matrix size becomes bigger and bigger. So if we have more antennas than which is normally the case, then it would be really complicated for a mobile phone to compute the matrix inverse. So it would require a lot of signal processing, and that would be power consuming, and your battery life would end up very quickly. So another possible option is that you can do the matrix inversion on the mobile on the mobile base station side. So what you can do is that you post multiply on the base station side, you multiply your signal S1 and S2 with H inverse. And when you have done it, so what you have actually transmitted not S1 and S2, but I call it S1 tilde and S2 tilde. And when this passes through the wireless channel, it just multiplies with the H inverse, the channel when it multiplies with the H inverse, and we know that the matrix multiplied with its inverse is equal to the identity matrix, and then identity matrix multiplied with a vector gives us the transmitted signal back. So it means that on the mobile station side, we don't need to do any processing, because the complicated task of matrix inversion has been taken over by the base station processing, and base station has more resources, so he can do that. So in this case, we can make a mobile phone simpler, and we can recover the signals, transmitted signal, without doing any further processing. So now, as I said, what if the matrices are singular, and what if and non-singular? What is actually the difference? So since I have shown, and we also know that we cannot do invert a singular matrix, so that means this matrix inversion method would not work in that case. So shows really that it is really important that a matrix must be non-singular, and that's why this knowledge plays an important role, that we should know whether the matrix is singular or non-singular. That's why you guys have been taught in the school to determine the singularity of a matrix. And now uh, let's assume a matrix, two matrices are non-singular, and but in one case the determinant is very low, which means that the matrix is very much close to singularity, and in one case the matrix is determinant is very high, and that means I would call with a slight abuse of notation, that matrix is far away from singularity. So what would be the difference? Here in this plot, I have shown the capacity So what data rate we can achieve if the matrices are different in their level of singularity. So if you can see actually that when the matrix is close to singular, the capacity is much lower. But a non-singular matrix has a very high capacity. So when you are having a very high data rate, that could possibly due to the case that maybe you are having your wireless channel is actually a very non-singular channel matrix. So now finally I will conclude uh, with this. So you have seen, I have shown you that matrix inverse is used in wireless communication transmitters and receivers. It is an integral part of a wireless communication system. We cannot imagine a wireless communication system without computation of a matrix inverse. So singular and non-singular matrices are very important. So you have studied in your school that there are singular and non-singular. So now today I have told you that actually a singular matrix and non-singular matrix, they are different in wireless communication in the sense that one demonstrates more capacity and data rate than the other. So in my next here I would conclude my lecture and my presentation, and in my next presentation I would try to give you further insight about the wireless channel, where you may understand actually the statistical behavior. So how a wireless channel in certain condition can result in a singular matrix, and in another condition a non-singular matrix, or perfectly a matrix with a perfectly orthogonal rows or columns. So what are those conditions? I will give you insight about that. So stay tuned with me and keep following my updates, and thank you very much for listening to me. If you like my video, don't forget to subscribe, and also don't forget to share it with your friends and family members who may have some interest in this topic.